Hello everyone. Today we're going to first introduce functions of several variables. We're going to go over some basics and then finally move on to partial derivatives, which is a very important concept in calculus. When you're dealing with functions of several variables, then you can differentiate the function with respect to different variables. Hence you get multiple derivatives, which are what we call partial derivatives. We're going to, in today's lecture, we're going to talk about, well, first how partial derivatives are defined, and then how they're computed, and finally what they geometrically mean. Let's get started. So the first thing is, what is a function of several variable? The name is pretty self-explanatory, so it's essentially a function that has more than one variable involved. Let me just give you two examples here. Since in this class we mainly focus on functions of either 2 or 3 variables, so I'm going to give you an example each. First, 2 variable. Say the variables are x and y, then a function f that depends on x and y equals x squared plus xy is a function of 2 variables. And similarly, for a function of 3 variable, we have f of x, y, and z, say equals x plus 2y minus 3z. So very straightforward. These are functions of several variables. Next, what's the domain and range? So the range, I'm sure you've encountered domain and range before, right? Domain is essentially the points at which the function is well defined. It makes sense. Range is the value the function can take. So the difference here is when you have one variable, the domain is usually an interval or union of intervals. But when you have 2 variables, the domain is typically an area. And when you have 3 variables, it's usually a volume. Now the range doesn't change. The range is still usually either an interval or union of intervals because the function it outputs only one value, right? Okay, let's see a couple examples. So the first one. Suppose we have a function f x and y equals square root of 64 minus x squared minus y squared. Let's look for the domain first. As we talked about, the domain is the points at which the function makes sense. Now, where does this expression make sense? A square root makes sense whenever the stuff under the square root is non-negative. So this function is valid when 64 minus x squared minus y squared is larger than or equal to 0. And plus x squared and y squared on both sides, we get x squared plus y squared is smaller than or equal to 64. So this is our domain, and you can see this is a circle, right, with radius 8. So this is what I meant by the domain of a function of 2 variable is usually an area. Okay, and what about the range? Well, the range is simpler. Since f is a square root of something and the only restriction is that the things underneath the square root is non-negative, so the range of a square root is just from 0 to infinity, right? So it's just from 0 to infinity, and that is the range. All right, let's try another one. Example 2. Again, two variables, f of x and y equals, say, ln of x plus y. Let's look for domain. Well, what's the restriction on ln? Ln makes sense whenever the argument following ln is, again, non-negative. So we need to have x plus y is larger than or equal to 0. Or equivalently, x is larger than or equal to minus y. Whichever way you want to write it is fine. Now the range. So let's look at the range of ln. Just like the 1D case, the argument that follows ln is non-negative. Therefore, the output of ln is all of real numbers. Okay, so the range of this function is the entire R. Okay, next we have contour map and level curve. For functions of usually two variables, for functions of two variables, we can define a contour map and the level curves. Now here's the definition. A contour map of a surface is created by projecting traces taken in evenly spaced planes that are parallel to the xy plane onto the xy plane. Each projection is a level curve. Now that sounds quite technical, so let's see what it actually means. Here's an example given in the textbook. Suppose this looks like a geological map. So suppose we have an area that looks like this. Okay. Then what we do is imagine it this way: we cut this entire thing horizontally at different heights, and for each height we put we put the cross section onto the map, and the resulting map is called the contour map. So for example here, when we cut sufficiently low, this little circle is the cross section, and that is this one right here. When we cut a little higher, say we get this cross section and this probably. Then on this contour map, we obtain this level curve. Okay, so each of these lines is a level curve, and when you put multiple level curves together, you get a contour map. This is quite useful in geology. So it gives you, say you have a large area. The contour map gives you a very clear representation of the height of each the height of every point. Not every point, but give you the heights of the area in detail. So just by looking at it, you can see that here is like a little valley in this area, and these are hills because you see the contour of greater heights concentrating here, and the contours here have lower heights. The heights are labeled on each level curve. So just by looking at it, you can tell this area has two hills on the left and on the right, and a little valley in the middle. So that's why we need these things. Okay, let's try to draw a contour map ourselves. Of course, we're not going to draw such a very complicated one like this. We're going to draw a contour map of a simpler function. First, let's draw the contour map of f of xy. Oh. 2xy. Well, when you're drawing the contour map, you have to pick specific heights, right? So I mean, the heights are what determine the level curves. So let's draw the contour maps at heights, say 2, 4, 6. 4 and 6. The more rigorous way would be to write at heights f equals 2, f equals 4, and f equals 6. All right, so first, let's look at the level curve. F of xy equals 2. Okay, now that gives us 2xy equals 2 and xy equals 1. Well, xy equals 1, you get x equals 1 over y, which is a hyperbola. And similarly, if you look at level curve fxy equals 4, you get 2xy equals 4, therefore xy equals 2, and x equals 2 over y. And then level curve f of xy equals 6, you get x equals 3 over y. Okay, so then you just draw the 3 level curves. Here's a coordinate system. X equals 1 over y is, it looks something like this. So probably like this. Oh, not a very good drawing. Okay, so it passes through the points 1, 1. And then for x equals 2 over y, so it's again a hyperbola, but it's slightly further away from the origin, like this. And if x equals 3 over y, it's even further away. Okay, the space is a little tight here, but you can label the curve like this, just 3, 2, 1, 3, 2, 1, like that, and similarly here, 3, 2, 1. All right. Let's try another problem. We have f of x and y equals so ln of x minus y, and draw the contour map with heights with heights 0, 1, 2. So I'm going to write f equals 0, f equals 1, f equals 2. It means the same thing as heights 2, 4, 6. It's just this is a clearer way of writing it. Alright, once again, let's look at the level curve. The first level curve. Ln of x minus y equals 0. Exponentiate both sides, we get x minus y equals 1. So x equals y plus 1. Let me add a page here. I think it's clearer if we draw the level curve one by one. X equals y plus 1 is a straight line that passes through minus 1, 0, and 1, 0. So suppose this is minus 1, this is 1, and you get this. This is the first level curve, and let's look at the second one. Ln of x minus y equals 1. Again, exponentiate both sides, you get x minus y equals e. X equals y plus e. It's once again a straight line, just slightly lower. It's a little bit more. It's not slightly, but it's lower. So like that. That's the second one. And the last one, the level curve ln of x minus y equals 2. You get x minus y equals e squared. You get x equals y plus e squared. Now, one moment. This is not a very accurate drawing, but so I want to give you a general idea what's the spacing between these level curves. So you have to know that E is approximately, it's 2.6, 2.8, it's 2 point something. So it's between 2 and 3. Therefore, E square is significantly larger than 1, right? So E square would be between 4 and 9. So you will find that the distance between the third level curve and the second level curve is larger than the space between the second and the first one. So we see that this should be the spacing between these two level curves should be larger than the spacing between these two. Okay, so that's the contour map of the second function. Okay, now we've gone over some basics of multivariable functions. We are in a good place to define partial derivatives. Let's start with partial derivatives of a function of 2 variables. You'll see that the partial derivatives of a function of 3 variables makes very little difference, but this is the simpler case, so we'll start from this one. Now suppose f of x and y, f is a function of the 2 variables x and y. Then the partial derivatives are defined as well, the first one, if we differentiate with respect to x, this is how we write that, df dx. Note that this is the cursive d. This is how we write the d in partial derivatives. When we have normal single variable function, we write, say g is a function of x only, then we write dg dx with the normal d. But when we are referring to partial derivatives, we write the cursive d. Okay, so df dx is defined as the limit of delta x go to 0 f of x plus delta x y minus f of xy. Oh, I forgot to write. Yeah. Df dx. It's again as a function of x and y. Okay, defined as this divided by delta x. And notice that it is very similar to the derivative in the 1D case, except now we just have a y hanging at the tail. Similarly, the partial derivative with respect to y, df dy xy, is the limit. Instead of adding a delta x behind x, we add a delta y after y. So the limit of delta y go to 0. F of x and y plus delta y minus f of x and y divided by delta y. Okay. Now there are a couple different notations for partial derivatives, and they are all equivalent. So let me write these out. Suppose again we have this function f of x and y, so it's a function of two variables. Then we can write it this way: f little x equals as a function of x and y. This is the partial derivative with respect to x. This is another notation for partial derivative with respect to x. So it's the equivalent to df dx. Sometimes we just use this because when the equation is super long, you get like 20 d's in equation, and it's just hard to read. So sometimes we just abbreviate it and write f sub x instead of the df dx. Okay, and so this is the two. This is one common notation that we use. And another thing is that if sometimes when we write say a z equals a function of x and y. This is, for example, when we have in three-dimensional space, we have suppose we have a solid. Then the height is a function of the x and y coordinate. So instead of writing f of x and y, sometimes we write, say, z equals 2x plus 3y. And when that's the case, we sometimes also write dz dx evaluated at x and y, or z sub little x at x and y these are all equivalent. They are once again the same as f sub x and df dx. Okay, and also sometimes instead of writing the parentheses x and y, we write a bar with x and y on the bottom. So what I mean is this: uh, sometimes we don't write dz dx as a function of x and y. We say dz dx, say evaluated at some number. And usually in this case, in this scenario, when we use this notation, we don't mean variables x and y. We actually pick out values. Say for example 0, 1. Okay, this is the same as dz dx 0, 1. So the only reason we do this is to make a distinction that we are picking out a specific set of values to evaluate this dz dx. You can also just write it this way. It's perfectly fine. So these two notations are very similar. Okay, these are the notations. One thing I forgot to mention. For example, when we are writing using the notation f sub x, we in general do not use this evaluation notation with the 0, 1 on the bottom. It's hard to say why. I guess it's just a tradition. We usually only use this when we have dz dx or df dx. Okay, now how do we compute partial derivatives? Of course, you can follow through with the definition involving the limit, or so there are two ways. First, just use the definition. And for example, we know a lot of the derivatives, right? So, for example, when you're differentiating x squared, you don't go through the entire definition. You just know the derivative is 2x. So we can do the same thing here. When you are computing the derivative with respect to x, you treat y as a constant. And if you're computing the derivative with respect to y, you treat x as a constant. Okay, let's see an example. Uh, let's see a couple examples. First, suppose we have this function f of x and y equals x times e to the x squared times y. Let's first compute the partial derivative with respect to x. As I said, when we're computing the partial derivative with respect to x, we treat y as a constant. Okay, so here, since this is the product of x and an exponential, we need to use the product rule. So the product rule says the derivative is the derivative of the first part times the second part, then plus the first part times the derivative of the second part. Now the derivative of x is just 1, so we have 1 times e to the x squared times y, and then plus x times the derivative of the second part. Okay, and that is to calculate this, we need the chain rule. So first we have the exponential, and then it's the derivative of the exponent. If you treat y as a constant, then you get 2xy, because the derivative of x squared is 2x, and then you just multiply by y, since y is a constant here. So we have e to the x squared times y plus multiply these two terms together, you get 2x squared y times e to the x squared y. So that's f sub x. Now f sub y is simpler because the first part x does not involve y at all, so that's just a constant. Right, so that's treated as a constant when we're computing f sub y. So it's just x times d dy of e to the x squared y. Once again, that is x times e to the x squared y times the derivative of the exponent, which is x squared. So you just get x cubed. Okay. All right, now let's look at a second. Oh, x cubed times, yeah, right. Let's look at another problem. Here, let's compute the partial derivatives of equals x squared minus 3xy plus y squared at, so evaluate the partial derivatives at the point 1 minus 1. Alright, so let's first compute the partial derivatives. Fx, f sub x equals, the derivative of x squared is 2x, the derivative of 3xy is 3y, so minus 3y, and the derivative of y squared, since we're taking the derivative with respect to x, then y squared is a constant, so the derivative of that is 0, right? So we get 2x minus 3y, and therefore the derivative at 1 minus 1 is 2 minus minus 3, so plus 3 equals 5. Let's then compute the partial derivative with respect to y. Same argument, x squared is constant, the derivative is 0. And the derivative of the second term is minus 3x. Then the third term becomes plus 2y. And plug in 1 minus 1. We get minus 3, then minus 2, so minus 5. Now we know the definition of the partial derivatives and we've seen how to compute them. Let's take a look at the geometric interpretation of partial derivatives. Recall that in the simple 1D case that you're probably used to, the derivative of the function at a point is the slope. It's the rate at which the function increases or decreases. So there's a similar interpretation here at play when we are dealing with functions of multiple variables. The only problem is because of partial derivatives, what exactly is the slope? Or what exactly does slope refer to, right? So if you have a surface, you start from a point, you have infinitely many directions you can go to. So what exactly does this slope refer to? Here, uh, we're going to draw the surface, and I'm going to show you what the partial derivatives geometrically represents. So first, suppose we are dealing with a function of two variables, because a function of three variables is much harder uh, to graphically represent, because if you have a function of three variables, you get three variables and then the function itself. So essentially, you get four things in total, and there's just no way to draw out four-dimensional system on a piece of paper because we live in a three-dimensional space. So a function of two variables is much easier to visualize, and that's what we're going to do here. So first, suppose f is a function of x and y. And we pick a point called x naught and y naught. Okay, so this is a point, this is fixed numbers, this is a point, let this be a point. In the domain. Okay, let me draw out the system first. So suppose we have a system like this. This is the y-axis. Oops, that's not straight at all. This is the y-axis, and then we have the x-axis, and then the z-axis. Probably don't need that tall. Okay, first let z equals f of x and y. Okay, so that way essentially we use f to represent the height, and x and y are coordinates on the flat surface. So then we make this into we turn this into a three-dimensional space, and f of x, y now becomes a surface. Okay, because for each point x and y you get a height, and that's exactly what a surface is. Suppose it's a surface that looks like this. Let me just draw a thing like this. It's a sorry, let me redraw that. Not the best drawing. Okay. Suppose we have a surface that looks like this, and this is the point x naught, y naught, and f of x naught, y naught. Okay, and let's define z naught as f of x naught and y naught. This is just so that we can write it out easily. So remember that this is the point x naught, y naught, z naught. Draw an arrow, x naught, y naught, z naught. Then what is f sub x evaluated at x naught, y naught? This is the slope of f at this point x naught, y naught in the x direction. Now, what does in the x direction mean? Well, first, let's go back to the definition. Remember that in the definition, we are incrementing x by a very little amount, because delta goes to zero, delta x goes delta x goes to 0. So we're incrementing x by very little, and then dividing the difference of the functions by this delta x. So here, what we're trying to say is it's the slope in which we only increase x naught, but not y naught. Okay, so it's something that looks like this. Suppose this dotted curve is let me erase that. Let me erase the x naught, y naught, z naught thing, since it's taking too much space. Suppose this dotted curve is given by f of x naught. Oh, sorry, I meant f of x and y naught. So we fix y as y naught, but we change x. If we only change one variable, we get a curve, right? This is a curve that lies on the surface and passes through our point x naught, y naught. So suppose this is the curve given, then the slope of this curve at this point is what we mean by the slope of f in the x direction. Okay, so geometrically, this curve is the intersection of the surface that we have and also the surface that's parallel to the xz plane. This curved surface is the surface given by f of x and y, and this vertical surface is a surface that's parallel to the xz plane. Okay, and that because we're fixing y as y naught, so that gives us a plane, a vertical plane that's parallel to the xz plane. So this is the curve. The intersection is the curve we want, and the slope in the x direction is the slope of this curve. And similarly, fy of x naught, y naught is, oh, let me just write this here. This is x direction slope of f at x naught, y naught in the y direction. Let me draw out the page. Yeah, let me draw a diagram for the y direction slope. So same surface. This is y-axis. This is x-axis. Z-axis. Okay, the same surface, the same point, but now in the y direction, we're fixing x as x naught, and we get this curve. Say this one. That is f of x naught y. So we are fixing the x coordinate as the fixed number x naught and changing the variable y. And this is the resulting curve. And this is also the intersection of this surface and a surface that is parallel to the YZ plane. Okay, so this is the diagram for the slope in the y direction. Yeah, so the slope of this curve is the slope in the y direction. Notice that this definition is exactly the same as uh, this interpretation is exactly the same as the interpretation of the 1D 1D case, because let me write this. This interpretation is compatible with the geometric interpretation of derivatives of functions of single variable functions. What I mean by this is, suppose you define a function g, let's call g of y, equals, let's say g of x, g of y, fine. Define a function g of y equals f of x naught and y. Okay, where x naught is the fixed number, as we said before, the x-coordinate of this fixed point. Then by definition, if you scroll back to the definition that we talked about earlier, you'll realize that g prime of y naught evaluated at y naught is the partial derivative of f at y, the partial derivative of f with respect to y evaluated at x naught y naught. Okay, so we can turn this partial derivative into a normal derivative, and we're familiar with the geometric interpretation of the derivative of a single variable function, right? So it's just the slope of the curve, and hence the slope of this curve, because f of x naught and y is this curve. So we see that the two interpretations are equivalent or compatible. Okay, let's see an example here. We want to find slope of the surface, oops, given by f of x and y equals minus 1/2 x squared minus y squared plus 25/8. And at the point, let me write this another line, at 1/2, 1, 2, in the, well, first x direction, leave a little space here. Then y direction. Okay, first you might be a little confused why we have three numbers, but this is a function of two variables. This is just because we are considering this as a surface, right? So think of f as the height or the z coordinate. So therefore, to define any point on the surface, you need the x and y and the z value. So what I'm saying is this is the x coordinate, and this is the y coordinate, and this is actually f. This is f of x and y. Okay, you. It's true that with the equation of the surface, you only need the x and y coordinate to determine the point. But since we're considering this as a surface, it's more intuitive, or it's more geometrically intuitive that we add f into the coordinate. So maybe I should change this. Is the slope of f at x naught, y naught, z naught. Where z naught is defined here. It can be computed from x naught and y naught. Okay, ooh, what's going on? All right, let's calculate this. We have our function f, then we take the partial derivative with respect to x, f(x) of x and y equals, so this is part 1, x direction. From what we talked about before, we know that the x direction is the partial derivative with respect to x evaluated at this point, right? So we first take the partial derivative with respect to x. We get minus x, and since y is a constant, so that becomes 0, and the derivative of 25/8 is once again 0. So that's just minus x. Therefore, fx evaluated at 1/2 and 1 equals minus 1/2. Okay, so this is the slope in the x direction. Now let's look for a slope in the y direction. Fy of x and y is minus 2y. Therefore, Fy evaluated at 1/2 and 1 equals minus 2. So So the slope in the y direction is -2. Alright, so that is all for the geometric interpretation. Now let's look at a few examples of functions of 3 variables. Functions of 3 variables are, functions of more than one variables are essentially the same. So you just have, the only difference is the number of variables or the number of partial derivatives you get. But the definitions are all similar. For example, of partial derivatives of functions of 3 variables is given by this. Suppose f of x y z, this is a function of the 3 variables x, y, and z. Then the partial derivatives, now since this is a function of 3 variables, we get 3 partial derivatives. So first is df dx, and then df dy, df dz. And all of them are, once again, functions of x, y, and z. This is the limit of delta x go to 0. Oops. F of x plus delta x yz minus f of xy z divided by delta x and df dy is the limit of delta y go to 0, f of x, y plus delta y, z minus f of x, y, z divided by delta y. And the last partial, df dz, is delta z go to 0, f of x, y, z plus delta z minus f of x, y, z So as you can see, it's pretty much the same as the two-dimensional case. Now when we take the partial with respect to x, we treat yz as a constant. When we take df dy, we treat xz as a constant. When we take partial with respect to z, we treat xy as a constant. Let's do a quick practice problem. Example, f of xy and z equals x times e to the xy plus 2z. Okay, so what is df dx? Once again, we can write this. So this is fy, okay? I'm not going to write it here, but you get the idea. So this is f sub y, this is f sub z, this is f sub x. So this is the notation I'm going to use simply because it's easier to write. F sub x is product rule. So derivative of x is 1. We get e to the xy plus 2z. plus x times the derivative of the second part okay, we get e to the xy plus 2z plus e to the xy plus 2z. Now the derivative of the exponent, since y and z are constants, is y. Okay, f sub y, xyz, x is a constant, so leave it as it is, and we get e to the xy plus 2z. Now the derivative of the exponent is x, because z is a constant, so the derivative of 2z is 0. The derivative of the exponent is just x, therefore we get x squared. And last, we get f sub z equals x times e to the xy plus 2z. The derivative of the exponent is just 2, so we have. The last thing we're going to talk about today is higher order partial derivatives. Just like the one variable functions, for one variable functions, you get, for single variable functions, you get second and third order derivatives. In the case of multiple variables, you also get second, third, fourth order partial derivatives. The only difference here is that the higher the order is, the more partial derivatives you get, as you see soon. First, let's talk about functions of two variables. The function f that depends on x and y. Now suppose they're all differentiable, then df dx, I'm going to skip the parentheses x and y here, but just keep in mind that they are all functions of x and y. df dx, df dy are both functions of x and y. So that means we can take more partial derivatives. Now if we take ddx of df dx, because df dx is a function of two variables x and y, so we get two partial derivatives here. We can take the derivative with respect to x, and then we can take the derivative with respect to y of df dx. Okay, and this can also be written as let me write that first. fxx. So so it means we're taking two partial derivatives with respect to x, and this is fxy. Note the order of the subscript and the order of the d's are opposite to each other, right? Because when we write it this way, we, just like the basic arithmetics of mathematics, when we compute what's in parentheses first. So that means we're computing the ddx part first. Therefore, here the little x is put first. Okay, and similarly, if we consider df dy, it is once again a function of x and y. Therefore, we can take two partial derivatives, ddx and ddy. and put in the subscript notation. Remember that we were computing the stuff inside the parentheses first, so we have f y first, then x, and this is f y y. Right, and sometimes you can also write d2 d squared f, and then dx dx, and this is dx dy, dy dx. Okay, these are all just these are three notations, three different notations of the same thing. So as you can see, for two variable function, you get four. These are all second order partial derivatives, by the way. So second order partial derivatives. So when we're talking about second order partial derivatives, it's not necessarily fxx or fyy. fxy and fyx are also second order partial derivatives. So as you can see, a function of two variables has four second order partial derivatives. Now if you continue taking higher order derivatives, for example the third order partial derivatives, since fxx is a function of x and y, you get two partial derivatives out of that, fxxx and fxxy, and so on and so forth. So it has 8 third order partial derivatives, and go on from there, you get 16 fourth order partial derivatives, and 32 fifth order partial derivatives, so on and so forth. Okay. All right, let's do a quick example. Let's compute the second order partial derivatives of this function. Of the function f of x and y equals 3x y squared minus 2y plus 5xy squared. Alright, to find the second order partial derivatives, we must first compute the first order partial derivatives. We get f sub x. Since we have so many of them, I'm just going to skip the parentheses x, y again. F sub x equals 3y squared plus, oh, what did I do? Oh, this is 5x squared. Otherwise, it wouldn't make sense. Yeah, this is 3y squared, and then the derivative of, well, y is consider y as a constant, so we get 5y squared times x squared, and you get the derivative is 5y squared times 2x, so that's 10xy squared. Okay, then fxx is take one more x derivative. Well, this becomes 0 because it doesn't contain x. The derivative of this is just 10y squared. And then compute fxy is equals 6y plus 20xy. right? Let me write 0. Okay, so these are the first two second-order partial derivatives. We have two left that are derived from f sub y. This equals 3y squared minus 2 and then plus 10x squared y. Oh, what did I do? I meant 6xy because x is the constant here. All right, take fyx. You get, take the x derivative on top of this, you get 6y. This becomes 0, and then plus 20xy. Fyy equals, take another y derivative on this, you get 6x, then plus 10x squared. So these are the 4 partial derivatives. Notice that here we have fxy equals fyx. This is in general true. Okay, it's not necessarily true for all functions, but it's usually for all the nice functions that you see, it will be true unless it's a piecewise function or something like that. So the rule is if the function has third-order partial derivatives, that is, it is 3 times differentiable. For example, it has fxx, fxxy, fxyx, all of that. Then this rule follows. But if it's not 3 times differentiable, then this may not be true. But either way, usually all the nice functions you see are 3 times differentiable. So in general, this is true. All right. So these are functions of 2 variables. Now what happens to functions of 3 variables? Let me just write this on a new page. Say f as a function of x, y, and z. Now, how many second order partial derivatives are there? Well, let's see. So we have fxx. Essentially, we're just arranging x and y, z in a length of 2. So we can the first derivative we take is x, the second again is x, or we can take first x and then y, or x and z. Oh, did I? X and z, and that's all the second order derivatives, with the first one being the x partial, and then we can take fyx, fyy, fyz, and then fzx, fzy, fzz. And that's all the second order partial derivatives. So you get 9. Right, you get 9 second order partial derivatives. And the way to compute that is exactly the same. Uh, I mean, except that you get more partial derivatives. That's what I meant by the more variables you get, the more partial derivatives you get. Um, we've seen how to compute partial derivatives of a 3-variable function. So now you just have to compute it twice. It's the exact same process except you do it twice. Okay, that's all for today. The web work has already been posted. I will see you all on Wednesday.